border gateway protocol builds routing tables by establishing persistent connections between peers over TCP port 179. But by default, BGP lacks native transport layer security. When a router receives a properly formatted TCP segment on this port, it assumes the packet originated from the configured neighbor. Without cryptographic checks, the control plane simply trusts the data. This architectural assumption leaves the session exposed. Off-path attackers can exploit this by injecting blind TCP reset packets or spoofing routing update messages to manipulate the routing table. Because BGP cannot inherently verify sender identity, securing the control plane requires forcing cryptographic authentication onto every single TCP segment exchanged between peers. This logic tree maps the attack vectors against a session. Notice the center pathway. To successfully execute a blind TCP reset, an attacker only needs to calculate or guess the correct sequence numbers for the active connection. Once the sequence numbers match, the targeted router accepts the spoofed packet as legitimate. It immediately tears down the BGP session and flushes all routing information learned from that peer. The immediate link failure is only the start. The resulting network flap forces traffic to reroute, potentially triggering cascading congestion across the wider autonomous system. Stopping this requires a mechanism that guarantees an attacker cannot generate a valid segment in the first place, even knowing the correct sequence numbers. For decades, the industry standard for cryptographic verification has been TCP MD5, defined in RFC 2385. The mechanism works by taking the TCP segment header, the payload data, and a single pre-shared secret key, then hashing them together to generate a 16-byte message digest. To understand the operational flaw, look at this diagram. MD5 architecture mandates a strict one-to-one relationship, supporting exactly one active key per BGP session. Updating the key for routine security compliance requires updating both peering routers simultaneously. If one engineer applies the new key before the other side is ready, the TCP handshake fails silently. The session is left stuck indefinitely in an active state. Because its reliance on a single static key forces network operators to choose between security compliance and network uptime, TCP MD5 is an obsolete standard. The modern successor is the TCP Authentication Option, or TCP-AO, defined in RFC 5925. It deprecates MD5 by integrating stronger, modular cryptographic algorithms like HMAC SHA-1 and AES 128 CMAC. This flowchart illustrates TCP-AO's core architectural shift. Instead of using one static password, the protocol defines a master key tuple, which generates a distinct temporary internal traffic key. The router combines this traffic key with the TCP segment to output a complex message digest. To ensure an attacker cannot capture and replay these segments later, TCP-AO also incorporates initial sequence numbers and sequence number extensions directly into the cryptographic digest. By generating unique traffic keys per connection and protecting against replays, TCP-AO secures the session far beyond the capabilities of MD5. More importantly, TCP-AO introduces a keychain architecture. A single connection can now hold up to 64 master key tuples simultaneously. This enables a hitless key rollover. When updating credentials, an engineer simply provisions a new key alongside the old one on both routers. Routers communicate their readiness to switch by setting the rNextKey ID flag in the TCP options header. Once both sides acknowledge the flag, the session dynamically transitions to the new key. The old key is then safely deprecated. By eliminating the downtime associated with key rotation, Hitless rollover allows networks to maintain continuous security compliance without destabilizing the routing table. Deploying TCP-AO requires a different approach. Unlike the single-line MD5 configuration, administrators must explicitly define a keychain object before applying it to the routing protocol. This comparison shows the exact syntax differences. Cisco IOS XE requires administrators to build a standard keychain, while Juniper Janos uses specific authentication keychain syntax. Once the keychain object exists, it is bound to the specific BGP neighbor or peer group within the protocol configuration block. This separation creates new deployment traps, like invisible text characters, trailing spaces in the secret, or mismatched key IDs. These cause silent authentication failures, keeping the session trapped in an active state. While TCP-AO solves the limitations of the protocol itself, it shifts the operational burden entirely to strict, standardized configuration management across the infrastructure. Cryptography guarantees data integrity, but it introduces a new bottleneck. Verifying AES or SHA hashes for every incoming packet consumes significant CPU cycles on a router's route processor. If an attacker executes a volumetric attack by flooding port 179 with thousands of spoofed packets, the router will exhaust its CPU attempting to cryptographically verify all of them. When the CPU maxes out, the router begins dropping legitimate BGP keep-alive messages. The session fails, even though the connection is cryptographically secure. Cryptographic authentication cannot protect the control plane from resource exhaustion. Defending the CPU requires a hardware-level filter that drops illegitimate traffic before it reaches the route processor. The most effective tool for this is the Generalized TTL Security Mechanism, or GTSM, defined in RFC 5082. It acts as a computationally cheap data plane defense. This diagram demonstrates the IP time-to-live header. As a packet passes through a router, its TTL decreases by 1. GTSM exploits this. Routers are configured to accept BGP packets from peers only if the TTL is exactly 255. Lower values are immediately dropped. An attacker located multiple hops away over the internet cannot spoof a packet that will arrive at the target with a maximum TTL. The hardware drops the malicious packets before they ever reach the CPU for TCP-AO validation. The only operational caveat is for interior BGP multi-hop sessions, where engineers must manually calculate and adjust the expected GTSM hop count. Robust BGP security requires a layered architecture. GTSM deployed at the network edge instantly drops remote volumetric noise, and TCP-AO deployed at the protocol layer cryptographically guarantees the integrity of the direct connection.